And with that, I think we're going to get started. We're going to take like a 10-second lead on this whole situation, and we're going to get started. And the title of the talk is, yes, you can run LLMs on Kubernetes. Who here was in this room for the last talk? Anybody stayed around for the last talk? And in general, who here knows that you can run LLMs on Kubernetes? All right, so yeah, then you don't need the talk. It's good. You all know. That's great. You can just tell other folks, and I didn't need to join a call now. That's good. jump back in. Yeah, so all of you know already, but let's do the talk. My name is Mofi, and I have my friend here,
Abdel.
And here today we're talking about it. So for those of you who already knew that you could run LLMs on Kubernetes, thank you.
You can now leave the room.
Yeah, that's good. But
for the rest of you, I mean, we're here to talk about LLMs because GenAI have been evolving over the last few years, right? And you all know about all these like very cool big models hosted by cloud providers that can do thousands and thousands and millions of windows, context windows. But we're here Kubernetes nerds, and we don't care about cloud-hosted stuff. We want to host stuff ourselves. And most of you will probably be hosting open LLMs, right? Which are also getting big. The DeepSeek model has, the R1 has 671 billion parameters. It's a 800 gigabyte model in a single file. And then all the other models that exist in the open world, we're debating whether we should keep open source because most of them are not, they're open weights. But most of these open weight models are getting big. They're getting complex, they're huge. Putting them in production is not easy. A very wise person, Clayton Coleman, had this statement saying, LLMs is the new web application.
Yeah, and if you are in the conference until Friday, Clayton actually has a keynote on Friday, and I have gotten a sneak peek that he might actually update this statement. So if you want to be the first to know what the new statement, what LLM is, you should check out the keynote from Clayton on Friday. But let's continue on. When you want to run LLMs on the cloud, you definitely have a lot of options, right? So you could do the old school bare metal, your server or VMs, manage it all yourself. And all the way on the other side, automated versions like Vertex AI, you have Bedrock, you have Azure Managed Services, or many other managed services. I believe Kubernetes sits somewhere in the middle, where it gives you kind of the control of managing your platform and your infrastructure, but also gives you the flexibility of auto-scaling and scaling to maximum and scaling down, getting access to a lot of resources, different resource types. So I think Kubernetes kind of does the best of both worlds in many ways.
And the reason is because we've been using Kubernetes for web applications so far, right? And it's great at doing that. All the stuff that Mofi talked about, the automation, the scalability, but also the device management. The working group device management have been doing a lot of great job, and the talk that was before us was actually explaining in details how the device plugin can help you plug a GPU into a node and make sure that your pod gets scheduled on the right node, the right GPU. In my opinion, one of the most important things that Kubernetes brings is the multi-cloud capabilities. Being able to deploy it in any cloud provider you want, and also having the kind of slide that Mofi showed where you have all the way manage yourself, kind of bare metal, to all the way using a managed service. If we take Kubernetes itself, we can also expand it, because you can also do all the way manage Kubernetes by a cloud provider to all the way manage it yourself. The value of Kubernetes is the standard single API for doing everything.
All right, so let's see some of this in action, right? So conference internet willing, we'll get to see some of these things in live. If it doesn't, we'll just fall back onto and act like that is the plan all along.
Yeah, we rely on you to just...
Yeah, just like act like it was the plan. Yeah. So the first things first, I'm going to try to write an YAML. That's my to-do, right? Fail writing this YAML from scratch and see how that goes. So we're going to create a Kubernetes deployment that is going to deploy a large language model on a cluster with GPU. We work for Google, so we have access to GKE, Google's managed Kubernetes services. We're also going to use something called GKE Autopilot that can automatically provision a new node with the GPU on demand instead of us having to pre-provision the node. So we're going to do all of that real time. So create a deployment. I'm going to let the Kubernetes, it's called ID extension on VS Code that lets me just create a scaffold deployment. So let's give it a name. The model I'm deploying is the Gemma 1 billion parameter model. So I'm going to give that name, Gemma 3 1BIT, instruction tune model. And then I'm going to name the deployment because I have too many of these things and I forget which one is what. And then I'm going to need an image. And I'm not going to memorize this image. I'm going to just copy it from one of the other deployments that I have here. So these are images that we provide as part of our Vertex. You could also grab any open image. So we're using vLLM as the serving engine right now. What that is, we're going to talk about in a second. But I'm going to use that image to get us started. Next up, I need resources. So we're talking about deploying a large language model. So the type of resource we need are GPUs. So let's give it some memory. So let's say about 20 gigabyte of memory, capital G, don't forget that one. I'm going to need about 4 CPU and NVIDIA.com GPU 1. And I'm also going to need some ephemeral storage because I'm downloading lots of data. I want to store them on my device somewhere. So I'm going to give some ephemeral storage, about 20 gigabyte. That's my limit. I'm going to copy the same thing for request. And should help me out there a little bit. Okay, here you go. Autocomplete is so great these days, so I don't have to. It's pretty good. And I'm going to copy a couple of other things from my other file that I have because I don't want to watch you all watch me fail typing. That's a long sentence. I'm going to just copy this command right here. All right, so the command basically is I have this vLLM-based image, which happens to have a Python file. I'm just running that with some arguments. So the arguments are my model ID, tensor parallel size is how many shards I'm doing the model. It's a small enough model that fits in a single GPU, so I only need parallel size 1. Host is just where I'm running, which host I'm running it at, and the port is 8,000. And my max model length is 32,000 tokens. So Gemma 3 1B has a max context window of 32,000 tokens. So let's do that. You also see I'm referencing an environment variable here, which I have to create now, which I'll also just go ahead and copy from here, which I'm going to need. And OK, so I have this environment variable called model ID, and I'm going to name it 1BIT. And this is the same name you're going to need. We're getting this from Hugging Face. So if you go to Hugging Face, you'll see like different model ID names. We're going to copy that one. And one last thing I need here is the Hugging Face hub token, because Gemma, like many other models like Mistral or Llama, is a gated model. So you're going to hear this term gated model a lot, is that these models are stored in Hugging Face or Kaggle, and you have to sign some sort of consent to say I am willing to sign this consent so that I can use this model. So I'm going to have my API token, which I already created the secret for, so I'm going to use that. And the last two things I need are volume mounts and volumes, because I want to store this model in a local storage as I download that. So I'm going to create that volume mount right here. Oh, token. All right, and the last couple of things is I need to have a port. And as you saw before, I was setting the port as 8,000, so I'm going to do the same thing as my port here. And this is the last part I need to be able to say this workload should run on a specific type of nodes. In Autopilot, what we do in GK Autopilot is, depending on the node selector, we can create the specific type of node for you. So we will go ahead and set that node selector. In regular Kubernetes, you can do the same thing because, again, this is a special type of device we're using, which is GPU. We want to make sure this workload runs against a specific type of node. So we'll copy that node selector, copy that in there. So that's my deployment done, hopefully. And then I'm going to need a service so that I can expose this deployment and so that I can talk to this model. And I'm going to create a service. And it's going to need a name. So I'm going to call it Gemma 3 1BIT service. And the selector is going to be Gemma 3 1B. Oh, I called it IB. No one caught it yet. Change this one too. Yep. 1. Here you go. And the port is, I'm going to expose the port 8,000, and I'm going to target port 8,000 as well on my deployment. So with everything there, hopefully I did everything right. If not, we'll find out together. So kube control, apply -f, K8s. The file is Gemma 3 1B it, itvllm.yaml. Send this in. What happened? Oh boy. Oh, server doesn't have a v1, so I maybe copied the server wrong. Or not.
It's a port problem.
It's a port problem.
Yeah.
Oh, volume 0 ports. You know what? Cut my losses, copy this in, and change things.
Yeah, let's just make it simple.
Yeah. And change all the names to 1B. Here you go, 1B here, 1B here, 1B here, 1B here, 1B here.
The joy of debugging YAML.
Oh yeah. I don't have my YAML engineer hat.
The service. Change the service.
No, service is the same thing.
All right, cool.
Okay, test it again.
That should work.
Maybe.
Hey, there we go.
Good. So I just ran this workload. Let's check what is happening with this. I'm going to do a quick watch. Kube control, get PO. And we're just pending. So what is happening right now, we're sending off this workload, and our GK controller is going to go ahead and create a new node, schedule my workload, and run this. So while that happens, we're going to continue on. We're going to come back to see what has happened here and some of the other fun stuff we could do with this.
Yeah. So one thing you might have noticed through this kind of example of very simple deployment is we said initially it's like LLMs are the new web app, but it's not a typical web app. This requires 20 gigabytes of memory and 4 CPUs and the GPU. You don't need this for a web application, right? And also requires storage, requires access to some sort of remote endpoint to download weights. So they are web applications are in the sense that Kubernetes doesn't really care. It just, here is a workload, give me some resources, and Kubernetes will allocate the resources. But they require some extra stuff. Before we move on, we figured we'd spend a little bit of time, because you're going to be hearing LLMs and a bunch of these words through in this entire conference. So we spend a little bit of time kind of equipping you with some basics, right? So LLM, I think everybody knows what that's, a large language model. It's a thing that can speak words, basically, right? That's very simple. Inference or serving. I have a very stupid example of explaining inference of serving. If you take a web application is a combination of CSS, HTML, and JavaScript, right? These three things are useless without a web server. If you want to render a web page, you need a web server that you can talk to, and it will serve you your web server, your website, right? So serving or inference, or sometimes we call it a model server, is essentially a piece of software that can render an LLM or render a machine learning model. It doesn't render it because there is no web page, but it's able to talk to the model using an interface that the model understands, and exposes an endpoint that you as an application can integrate with. That endpoint is usually REST, and then the model talks something that depends on the architecture of the model. So whenever people say serving, inference, or model server, they usually refer to vLLM. That's what Mofi used, but there are tons of open source ones in the market, and we're going to talk about them. Accelerators, pretty straightforward, GPU, TPU, or this new thing called Grok. Essentially, any sort of special hardware that is really good at doing matrix calculation or matrix multiplication.
Yeah, and some of the other things you're going to hear quite a lot is quantization. So when I said a model is like a 1 billion parameter or 10 billion parameter, what we were saying is there's 1 billion numbers in there. And that number could be on the full 32-bit precision, or it could have less precision and have less memory footprint. So it could fit a much larger model in a smaller GPU if you use a lower precision of using quantization. With quantization, you kind of give up some of the quality of the model to be able to fit a larger model. So there is like a trade-off you have, but you get to fit bigger models. Weights are just what I said, the numbers that I have, the model, how the model represents the world around it are the weights. Context window is how many tokens you can fit to a model in a given time. For example, something like Gemini can have up to like 2 million context window. Our open models like Llama, Gemma has up to 128K context window, which is quite a lot, but if you're trying to process videos and such, it's probably not going to be enough. And finally, multimodal. So the models we're dealing with here are all text to text. You send text, you get text back, but something like Stable Diffusion, you can send text and get image back, or send text, get video back, or send an image and get text back. So you can have a lot of this A to B situation going on. And when you talk about model servers, we just looked at vLLM, but that's not the only one. There is many of them in the market right now. TGI comes from Hugging Face. So Hugging Face is where we're getting our model data from. They also provide you some software to run these models yourself. NVIDIA, again, they're the biggest provider of GPU at this day. And so they also have a software in the market called NIM, which is, I think, proprietary. They don't have an open source component all that much yet, but it's built on top of open source standards. You have Ray Serve. So Ray, you can probably hear about it or look it up. They are purpose-built for distributed workload. So model serving is kind of a distributed workload they're really good at. In the world of TPU and also GPU, you also have JAX, which is Jetstream. JAX is an open source project coming out of Google. And a lot of people can run models locally in Ollama, but you can also run Ollama as a container on the cloud. So you can kind of bring your own home experience into the cloud very easily with Ollama. And as you're doing this, one other reason this large language models are not like your typical web app is the size of the container image. Over the last 10 years, we kind of preached to the choir and told people to let's make containers smaller, let's bring small containers that are very portable. All of a sudden, 2022 happens, and vLLM image is like 10 gigabyte. And all the learnings we had, it goes out the window. Like, how do you now run this giant model into our container and on our cluster? If you're trying to download a model of that size on the public internet, you're looking at times anywhere from 2 minutes up to like 10 minutes. Because again, you're going off to the public internet to download all that image data. You also have the size of the model to how much GPU memory you need comparison. So easy way to run the math is that if you run it on full precision, you are going to need twice the memory. If you run it in half precision, it could run in less memory, right? Sorry, if you run it in full precision, 1 bit becomes 4 bytes, right? One number becomes 4 bytes, so it requires 4 times the GPU memory. So if you have a 4 billion parameter model in full 32-bit precision, it's going to require you to have 32 gigabytes of video memory. Most of the models you're going to see run on the internet is going to be something like BF16 or FP16, which is like 16-bit precision, which only requires double. So if I have a 27 billion parameter model, I'm going to need roughly around 54 gigabytes of GPU memory. So with the same math, you can see DeepSeek.
Yeah, so you can see here DeepSeek at full precision is 1.37 terabytes. That's how much memory, GPU memory you will need if you need to run DeepSeek. Today on the markets, there is no GPU that has this amount of memory. The biggest GPU you can find on the markets is an H200, which has 80 gigabytes of memory.
H200 has 141, H100 has 80.
Thank you. H100 is 80, H200 is 140, right?
Yeah, even with that, a single node of H100 or H200 does not have, like, you can have a single node with 8 H100 GPU, still doesn't have enough memory to fit DeepSeek R1.
Because there is also something to keep in mind is there is sometimes a physical limitation into how many GPUs you can fit on a single node. And that typically depends how many PCI Express ports are available on that node, which typically is 8. So let's say we take an example of an NVIDIA A100 with 40 gigabytes of memory. If we take a node and we fill it with A100 GPUs, we can only do 40 times 8, so that's 320 gigabytes, right? So if we want to run something like DeepSeek, which is 1,370 gigabytes, we need more nodes. So the kind of variations you're going to see in this space are either what Mofi did, single host, single GPU, or single host, single accelerator, or single host, multi-accelerator. You remember earlier when Mofi was deploying, there was this sharding parameter, which he set to 1. You can also set it to 2, 3, 4, 5. And that's essentially the sharding, the splitting of the model across multiple GPUs. But then you might also be faced with a situation where you cannot fit the model on a single node and you need to split it across multiple nodes. And that's the third situation, which is multi-host, multi-accelerators. Now, the two first ones, Kubernetes can support them out of the box. The third one can only be supported through this new API called LWS, or Leader Worker Set. So the Leader Worker Set is a new API in Kubernetes open source that allows you to define a leader and a set of workers where the leader distributes the shards and the workers run the actual model. So the sharding is done by the leader, and then you have multiple nodes, and that's how you're able to do multi-host, multi-accelerators.
Yeah. So if you want to learn more about this, there was a talk by one of the maintainers of Leader Worker Set in the last KubeCon in North America. You can go find that talk on YouTube. Do not watch that now. We're still talking.
Yes.
So when you're trying to run large language models on a Kubernetes cluster, it is like, as we said, there are multiple dimensions of optimization we could do, right? Number one is the image size has gotten really big, so we could do some optimization to make sure the images are cached on the nodes before. You could do some optimization on the data layer. Downloading the model every time from Hugging Face is expensive operation. Can we do something to pre-cache those model data somehow? Or download it one time, and for every other consecutive runs, we can just use the same downloaded model. And there's also like workload scaling. We can do some work on the cloud level or your infrastructure level to scale that workload more intelligently rather than just like having a bunch of GPU just sitting around just in case you need it. So there are a lot of optimizations that are happening. This talk is probably not the right place to talk about all of this. We'd be more than happy to talk about like if you have a specific need of that kind, or what are we doing in the open source to kind of handle that situation. But let's move on to check out what is happening with my demo if it's still figuring things out. Here we go. I think we stalled enough for the GPU to like figure it out and run everything. I'm going to quickly go ahead and give a quick logs. What is the name? Let's go.
It's that. Oh, no.
Okay, I'm going to have to do
Get spots.
Okay, get PO. I have to copy the name. Oh, it started with vLLM. Okay. What did I do? Oh, kill logs. Get me on stage and I forget everything. There you go. Run this. And at the end of everything, we can see that about a few minutes ago, it took about 4 minutes for it to download everything and start the vLLM server. right? Now I have a server ready here. I could also do get service, and I would see that I have a service ready to go. I could like set up a load balancer on top of it to talk to it. But I thought what would be fun for all of us today, actually, instead of just talking to one model, what if we talk to a bunch of models? I have a different namespace in default, and I, over the last couple of days, deployed a bunch of these large language models. So if I do get service, you would see a bunch of these large language models that are currently running. And then what I thought would be very nice for us to be able to chat with all these models at the same time. So I built a small little UI tool. And I can go here, and I can show you the URL for this. Actually, I will show you this one on the right is going to take you to a UI, where it's going to have a text in box where you can type in your prompt. One on the left is all the code that builds this. So if you want to go check out the code, you could do that later. But one on the right is where you want to go. So together, we're going to do one simple prompt here. OK, everybody got the phone out? Everybody got it? Don't all yell out at once? OK, cool.
We'll see if it scales.
All right. Yeah, probably not, because I didn't set up any auto-scaling. I could have, I didn't. I'm going to quickly run this one prompt, which worked really well last time. So let's see how that goes. Tell me, knock, knock, joke. Use, because we're in London, use elements of British humor. I thought, like, we're in London right now. We should use that. And send this prompt across all these models at the same time. You can all try that in your own phones if you scan the token. And this came out one time before, too. It's one of my favorite jokes now. I'm going to read it out for all of you, OK? Tell me a knock-knock joke. Use elements of British humor. OK. So I'm going to say the knock-knock part. You can say the other part. OK, let's go. Knock-knock. Who's there? Arthur. Are there any biscuits? Right. So again, all of you have this like a tool right now. I'm going to keep it running for probably the rest of the week. So if you want to like keep testing a bunch of different LLM models at the same time, you can. But let's take a look at how all of these models are being served. We talked about vLLM, but we actually can use a bunch of different serving engines. So we have vLLM for one of them. For the Gemma 12B that you are seeing on your screen right now, if you have the phone up and running, we're using Ollama. So we're just basically packaging Ollama with the Gemma 12B on it. We're running using Ollama. For the 3B version of Llama 3, we're using TGI. So you can just package everything in a TGI container, use that model, and have that running that way. Yep. You might be wondering, hey, you work for Google. I heard you guys have TPUs. Are you doing anything with TPUs? Yes, we are. We're deploying the Llama 3 8 billion version on a TPU. And one funny thing you might have noticed that you are talking to, on a single interface, you're talking to all these different models. It's fully transparent to you, the user, that you are talking to a TPU or a GPU, because underneath, we're using vLLM with TPU, and it gives the same exact API interface. That's the big point of using these models. We're also deploying Mistral. Again, one thing I think Abdel mentioned about like a DeepSeek being a really large model. How do I go about doing this? All of you are probably itching to learn about LWS. I have you covered. You can go to DeepSeek R1 folder. Again, this is a bigger model. It requires a little bit more things to be able to handle things a little bit better. So you have this DeepSeek R1 using Ray and vLLM together. We're setting up this thing called the leader, which is starting as a single worker, has 8 and H100 GPU on it, and setting up this vLLM worker using Ray. So I'm setting up a Ray worker that can now say, OK, everybody else under my control, send me your work. And then I have a worker template, worker pool, which is also a single H100 node with 8 GPUs. So I have 2 node total that is doing the work. I have 16 H100 GPU do all the work. Yeah. And that is basically sending its work back onto the leader worker, right? So together, they're basically computing every time you send a request, the R1 model is sending. So in the list, I think the last model is the R1. So you can see that working. Couple of other things we talked about, like optimization, is that when you're doing like such a big model, which is about 800 gigabyte of download, you don't want to go and download it every time back and forth. So we're using something called HDML, which is a Google Cloud specific thing, but you could do a specific thing like this in pretty much any cloud, where you use extra storage or PVC to store the model data. So we're doing that here. Instead of actually downloading the model every time, we're just mounting this volume that we can talk to it. So yeah, we have all of this example. If you got the GitHub repo, you should be able to actually, the one on the left, if you want to scan that real quick, all the YAMLs and all the things we use, including the UI, is actually open source. You can go try and play around with it.
Yeah, unfortunately, we don't have enough time to go through all the details. One thing that we didn't really show is actually with Ollama, you can see, and Ollama is one of the ones that you can try this very simple do I download the model, right? When you do Ollama app, the model get downloaded, or you can pre-bake the model inside the image and then produce a new image that already contains the model. That's one thing you can play with to see kind of like the alternatives and kind of see which one starts faster. But basically, we thought we would wrap it up with showing this reference architecture for AI platforms. And the whole point of this talk was to say, yes, you can run LLMs on Kubernetes. Kubernetes is the bottom layer where you can run pretty much everything. And the project is doing a lot of work to actually make it possible to do more things with LLMs. So you have the typical stuff like the auto-scaling. You have this open source project called Q, which we open source, but you can use it anywhere you want. It's a Kubernetes native job queuing system. You have all your multi-tenancy infrastructure as code, GitOps, like your DevOps way of doing things. So if you're doing DevOps for web applications, you can also do the DevOps for LLMs. And then at the bottom layer, you have your multi-instances, like the way you share instances on the same nodes or across nodes. You have access to your hard drives, volumes, as Mofi showed. You have this thing called Fuse, where you can mount a bucket. It doesn't have to be a Google Cloud bucket. It can be any bucket. The Fuse driver supports multiple types of buckets. And then
yeah, and finally, like the blue-colored box, I don't know if the color shows, it does, fantastic. The blue-colored box is kind of like what Kubernetes cares about. Anything outside is a software you could run pretty much in your control. It could be your own custom like machine learning application. It could be any of the open source tool you could just grab from the internet anywhere. So for that part, a lot of the decisions, like how those apps are built, is outside of Kubernetes' control. So we are actually working with the community quite a lot to make sure that any type of app that you want to run on Kubernetes works, and we've been doing this for the last 10 plus years at this point. So again, the community is evolving. We're seeing a lot of changes from data scientists to like machine learning engineers, and Kubernetes, we want to make it the best place to do this kind of workload. With that, we're gonna give you this QR code. This is to send us any feedback. Feedback is a gift. Anything you liked, and this also lets CNCF know if this type of a talk is useful for you to learn. And I don't think we're gonna have much time for question answers. I don't think we have a mic running or anything, but we're gonna be here around. If you don't find us here, we're gonna be in the Google booth. So if you have any questions.
There is actually a mic.
Oh, there is a mic, fantastic. Yeah. But we have only 4 minutes. I don't know if we have much time, maybe like 1 or 2 questions, or just find us after the talk outside here, anywhere. If you have any type of questions about running machine learning models for serving use cases or training use cases. Yeah, thank you so much for joining us.
Thank you.